Hi everyone, this is Dr. P. Rajkumar, Assistant Professor, Department of Mechanical Engineering. Welcome to Machine Design course. The topic for today's discussion is design of shafts subjected to bending and twisting moment. The aim of the present session is to design of shafts, to discuss about design of shafts subjected to bending and twisting moment. So what are our main objectives for this session? The first objective is to discuss on the design of shafts subjected to bending moment, and the next one is design of shafts subjected to twisting moment. So at the end of this session you will be able to understand the concepts related to both these concepts. So let's start the discussion. Okay, what do you mean by shafts? So shaft is nothing but it is a rotating machine element that transmits the power. Now you can see here, like the power which is generated in the through motor is transferred to driven machine using this rotating member. This rotating member we are calling here, it is a shaft. So if you see the cross section of these shafts, it is in the circular cross section. So normally in general the circular cross section is used for the shafts. Why we are using is because of high sectional modulus and its capacity for the twisting moment. So these are the two major reasons why we will use shafts in the circular cross section. So and coming to the classification of the shafts. The shafts can be classified into two major categories. First one is the transmission shafts, another is the machine shafts. Like transmission shafts, the name itself is indicating transmission, the shafts which are used to transmit the power from driver to the driven. They are called transmission shafts. The examples are like counter shafts, line shafts, and the another category of shafts is machine shafts. So these are the integral part of the machine itself. If you see the one of the example is the crankshaft. So the crankshaft will be integral part of the machine. Similarly another one is the camshaft. These are also integral part of the machine itself. And coming to the what are the common materials used for the shafts. So most of the shafts will be manufactured using mild steel, and wherever the high strength required for the shafts, there we will be using alloy steels such as nickel chromium or chromium vanadium steels. And the manufacturing process used for the shafts fabrication is generally hot rolling, and the cold rolling will be used to the finishing of the size, and turning and grinding operations also will be used to finalize the shaft diameter and its surface finish, everything. And coming to the standard sizes of the shafts. First of all, why we have to manufacture or fabricate the shafts in some standard sizes? The reason behind this is in order to facilitate the exchange and interchange facility throughout the world, throughout the globe. For example, assume a situation you have fabricated a shaft in India which is not a standard size, but now you are incorporated the shaft in the one machine which is being used in Australia. If that size itself is not standard, then if any part to be replaced, then it will be very difficult to replace that part. So in order to avoid all those challenges, there are some standards like ISO standards, ASME, ASTS standards used for the standard sizes of the shafts. So coming to the machine shafts, that means which are integral part of the machine. Generally they are fabricated or manufactured up to 25 mm steps in the step size of 0.5 mm. That means 0.5 mm, 1 mm, 1.5, 2.5, like that. Similarly the transmission shafts, they are starting from 25 mm to the 60 mm with 5 mm steps. That means 25 mm, 30 mm, 35, 40, 45 and so on up to 60 mm. And there is similarly 60 mm to 110 mm with the step size of 10 mm. Similarly from 110 to 140 the step size of 15 mm. 140 to 500 with the step size of 20. That means 140, 160, 180, 200, like that. So the standard lengths, now all these are the diameter of the shafts. So the standard lengths of the shafts are like 5 meters, 6 meters and 7 meters depending on the application of the shafts where we are using. Our topic here it is design of shafts subjected to twisting moment and bending moment. So let's consider when the shaft will be subjected to the twisting, that moment, that means shear stresses, because we know that the shafts are majorly used to transmit power from driver to the driven member. So because of this transmission of torque, the shafts will be subjected to the shear stresses. Next, the power is transmitted from driver to driven using the support of some rotating members like pulleys, gears and bearings. So during the operation, some loads will be, or loads or forces will be acting upon these members such as pulley and gears. So because of loads acting on these members, this shaft will be subjected to bending stress. So what are the two major reasons why the shafts are subjected to twisting moment and bending stress? Twisting moment is because of the transmission of the torque, and bending stresses are due to the load acting on the supporting members such as pulleys and gears. So now we will see how to design a shaft when it is subjected to both the conditions. So while considering the design of the shafts, there are majorly two criteria. The first criteria is we have to design the shafts based on the strength criteria. Another is the stiffness, rigidity and stiffness criteria. That is strength. What is the meaning of the strength? It is the maximum load carrying capacity, or it is the ability of the strength. It is the ability of the one material to cut another material. That is and stiffness. It is a load per unit deflection. That is stiffness. So here we will be designing the shafts based on either strength criteria or stiffness criteria. So whenever we are following the strength criteria, these are the majorly 4 different criteria that the shafts will be subjected. First one is the shaft subjected to that only twisting moment. Second criteria, shaft subjected to only bending moment. Third one is the combination of both bending moment as well as the twisting moment. Fourth one is the in addition to twisting and bending moment, the axial loads also will be acting upon the shafts. So these are the different, these are the 4 major criteria that the shafts will be subjected to loadings. So now we will see one by one, and the first one is the shaft subjected to the twisting moment. So whenever a shaft is subjected to only twisting moment, we have to use the torsion equation. This is called the torsion equation. What is the torsion equation? T by J is equal to tau by R. Here T is the twisting moment, tau is the torsional shear stress, J is the polar moment of inertia. And by substituting all the values for the circular cross section, for circular cross section the J value is equal to pi by 32 d power 4. So by substituting all the values in this equation and R is equal to d by 2, we will get the equation like twisting moment is equal to pi by 16 into tau into d cube. This equation is for the solid shaft. If the same shaft, if the hollow shaft is subjected, then the equation can be written like twisting moment is equal to pi by 16 into tau d naught power 4 minus dA power 4 by d naught. This is the equation for a hollow shaft. This is the equation for the solid shaft. In order to calculate the twisting moment, we know that the power transmitted by shaft is equal to P is equal to, we know that P is equal to torque into omega. So, and we know that this omega is equal to 2 pi n by 60. So by substituting both of these values into the P is equal to T omega equation, we will get power is equal to 2 pi n T by 60. From this equation, if you know what is the power transmitted by shaft, you can calculate the twisting moment from this equation. Next criteria is shaft subjected to only bending moment, and this is called a bending moment equation, like m by I is equal to sigma b by y. Here y is the distance from the layer to the neutral axis, and I is the moment of inertia, sigma is the bending stress, m is the bending moment. So by substituting all the values, I is equal to pi by 64 d power 4 for a circular cross section, by substituting this value in the given equation, we will get the bending moment is equal to this one. The same equation for a hollow shaft can be written like this one, and where k is equal to di by d naught. Di is the inner diameter of the shaft, d naught is the outer diameter of the shaft. So this is the second case. Now coming to the third case. What is the third case? The shaft subjected to combined twisting moment as well as the bending moment. This is the third criteria. So in order to, whenever we know that whenever more than one kind of load is applied on the machine members, then we have to use the theories of failures to find out its design stresses or its design values. Now according to the maximum shear stress theory, whenever the stress developed inside the member exceeds the allowable limit, then it subjects to failure. So according to the maximum shear stress theory, the tau max is given by half into under root sigma b square plus 4 tau square. Here sigma b is nothing but your bending stress, tau is nothing but your shear stress. Why we are getting this bending stress? Because of the bending moment. Why we are getting here tau value? Because of the twisting moment. So this is the equation we have to use while designing a shaft subjected to both the twisting moment as well as the bending moment. Now by substituting all the values by sigma b, now how we can write from this sigma b value? 32m by pi d cube. So sigma b is equal to 32m by pi d cube. Substitute that value in this equation. Similarly tau also you substitute, and finally you will get the equation tau max is equal to this one. This is equation is almost similar to your equation like torque is equal to pi by 16 tau d cube. So if you see here, from this I can write the tau max is equal to 16 by pi d cube into 16 into t by pi d cube. So here this equation if you compare, here this equation if you compare, the tau max is equal to 16 by pi d cube into this term. So this term we can write here, this is equal to Tg, that one we will call equivalent twisting moment. Equivalent twisting moment we will call Tg, that is nothing but Tg. So equivalent twisting moment. Now what we can write? A shaft subjected to both twisting moment as well as bending moment, what we can write? Pi by 16 into tau max into d cube is equal to under root m square plus t square. M is nothing but bending moment, E is nothing but twisting moment. Now coming to the another one, according to maximum normal stress theory. According to this theory, the failure when it happens, whenever the stresses developed inside the material exceeds the allowable normal stresses, then the failure will happen. So according to this theory, we can derive half sigma by 2 plus half sigma b square plus 4 tau square. How did we get this equation? Sigma 1 principal stress is equal to sigma x plus sigma y by 2 plus or minus under root sigma x minus sigma y by 2 whole square plus 4 tau square. According to that equation, and by substituting sigma y is equal to 0, we will get this equation. Now by substituting sigma b values as well as the tau values from the previous equations, we will get this is the final equation. In this one we will call, this equation we will call equivalent bending moment, ME, we will indicate with the ME, equivalent bending moment. So by substituting this ME value, here ME is equal to equivalent bending moment, and substituting this one, we can calculate the diameter of the shaft subjected to both bending moment as well as the twisting moment. So in conclusion, what we are saying is, whenever a shaft is subjected to both bending moment as well as a twisting moment, either you can use maximum shear stress theory or maximum normal stress theory to calculate the diameter of the shaft. So let's consider one problem. Now I am taking one problem. A shaft made up of mild steel is required to transmit 100 kilowatt at 300 rpm. The supported length of the shaft is 3 meters. It carries 2 pulleys, each weighing 1500 newtons, supported at a distance of 1 meter from the ends respectively. That means from the left end 1 meter, again right end also 1 meter. Now assuming the safe value of the stress, determine the diameter of the shafts. What they are asking? They are asking you to calculate the what is the diameter of the shaft. Now if you see here, since it is easy to transmit the power, so what is the power here? P is equal to 100 kilowatt. So power is given, already N value also given, so 300. So we know that the equation is equal to power is equal to 2 pi nt by 60. In this equation power is given, n also given, only the unknown is the twisting moment. So you will get the twisting moment from this equation. And now coming to the bending moment, how we have to calculate, because the shaft is subjected to here 1500 newtons, 1500 newtons load from both the loads. So the bending moment will be RA into this 1 meter. So since it is a simply supported beam, we will get the value as RA is equal to RB is equal to same 1500, we will get it, because it is like simply supported beam. How we can write RA plus RB is equal to 3000. From that equation we will get the RA is equal to RB is equal to 1500. So now coming to what is the maximum bending moment, M is equal to, now coming to the maximum bending moment value, one second I will show you. So now what is the maximum bending moment, M value here 1500 into 1 meter. So you will get 1500 Newton meter. This is ML. M is given, torque is, twisting moment also given. So whenever both the values are given, we know that what is the value, we know tau max is equal to 16 by pi d cube into under root m square plus t square. This is according to maximum shear stress theory. So here the twisting moment known, bending moment also known, tau max. Tau max is not given, but they have mentioned the mild steel material. So what is the, you take the allowable material as tau max value, maximum shear stress value for the mild steel material as the 60 MPa. So you take, you know now tau max value you know, m value you know, t value also you know, only the unknown is the diameter. So using this equation you can calculate the diameter of the shafts. So this is how you have to calculate the, or you have to design the shafts whenever it is subjected to both bending moment as well as the twisting moment. Next, similarly there is one more problem. A mild steel shaft transmits 20 kilowatt power at 200 rpm. It carries a central load. Now this problem it is given central load, instead of simply here they have simply given it is subjected to some 900 newtons and it is subjected to the simply supported one between the bearings and 2.5 meters apart. The distance between these two is 2.5 meters. So now they are asking determine the size of the shaft if the allowable shear stress, that means tau max value they have given already, tau max is given and compression stress also given. So we will try to calculate according to maximum shear stress theory only, we will try to calculate. So this value is enough 42. So now in order to calculate the bending moment, first we should know what is the reaction loads here. So RA and RB value I can write W by 2. So correspondingly the bending moment will be W into L by 4. So W is nothing but 900 Newton, L is nothing but your 2.5 Newtons. So you substitute both the values here, you will get the bending moment value. And how you will get the twisting moment value, again just now only we have seen power is equal to 2 pi nt by 60. Here n is given 200 rpm, power is given 20 kilowatts, so only unknown is twisting moment. Once you know bending moment, once you know twisting moment, again how you can calculate, the tau max is equal to, how did we calculate just now, 16 by pi d cube into under root m square plus t square. M is known, t is known, tau max known, only unknown is the d. So you can calculate the equations according to this one. So this is how we have to design the shafts which is subjected to both bending moment as well as the twisting moment. So now what we learned, a shaft subjected to bending moment as well as the twisting moment, how to design a shaft we have learned. And you can refer, these are the different textbooks, you can refer all these textbooks for the further learning, and thank you.